Welcome. This video is a brief introduction to differential equations. In a nutshell, a differential equation is an equation that contains a derivative. And we'll discover in this portion of the course that differential equations are a very powerful tool for modeling many different phenomena. For example, let's take a look at this differential equation. Here we have a derivative, and in this case, this is a model of population growth. P is standing for population, and this is saying that the rate of change of population, the derivative of population with respect to time, is equal to some constant k times the current population. This is saying that if we want to know how fast a population is changing, that's the derivative of the population with respect to time, the rate of change of population, well, it's proportional to the current size of the population. And if we think about this, this makes a good bit of sense. The larger a population is, the faster it will be growing. So the rate of change of population is equal to a constant times the current population. So this is called a differential equation. It's an equation that contains a function and one or more of its derivatives. There's a second part to this example here. This is called an initial condition. And this is saying that the population at time t equals 0 is equal to 100. In other words, when we start examining this population at time 0, there are 100 members of the population. When we have a differential equation along with an initial condition, this is called an initial value problem. That's a term that will come up from time to time with differential equations. It's called an initial value problem. Now, we would like to know what is an equation that models the population. This is just a description of the population growth, but what would be an equation that models the population? Well, that's called the solution. And for this example, the solution is the population at any time t is equal to 100 times e raised to the kt power. This is the solution to this differential equation. It's a function, and if we were to take the derivative, dp dt, we would see that the derivative is equal to k times this function. This function satisfies the differential equation. Let's talk a little more about some differential equation terminology. A differential equation, as we've been discussing, is an equation that relates some unknown function to one or more of its derivatives. The solution to a differential equation is a function, and the function must satisfy the differential equation. Another term that we use for differential equations is the order. The order of a differential equation is the highest order of a derivative that could appear in the differential equation. For instance, we have a first order derivative in this differential equation, so this is a first order differential equation. Let's look at some more examples. Here we have a function s of t, which is describing the position or the height of some falling object at time t. On Earth, if we ignore the effect of wind resistance, a falling object experiences a constant acceleration of approximately negative 9.81 meters per second squared. We would like to come up with a differential equation that models this phenomenon. Now, acceleration is the second derivative of position. The first derivative is velocity, the second derivative is acceleration. So, acceleration, that is the second derivative of the position function, which we can write using this notation. So we have the second derivative of the height, that's the acceleration. It is a constant value of negative 9.81 meters per second. This is a second order differential equation because we have a second derivative. And we could solve this differential equation. We won't discuss the details, but if we were to solve this differential equation, the solution is the position function. It is negative 9.81 over 2 times t squared plus v sub 0 times t plus h sub 0. V sub 0 is the initial velocity of the object, h sub 0 is the initial height of the falling object. So from this differential equation, there are methods for finding the solution. Once again, this is the differential equation. This is the solution that satisfies the differential equation. Let's look at one final example. Lake whitefish grow to a maximum length of 22 inches. There's a description about the growth rate of a whitefish called von Bertalanffy's equation. It states that the rate of growth is directly proportional to the difference of the fish's current length and its maximum length. We would like to write a differential equation describing this observation. So we're thinking about the growth rate of a fish, and the current length of a fish is L. So the rate of growth we can describe with a derivative. The rate of growth is the rate of change of length with respect to time. That is the derivative of L with respect to t. So growth rate, that's the rate of change of length with respect to time. And we're told that the rate of change, or the rate of growth, is directly proportional to the difference of the fish's current length and its maximum length. That difference is the maximum length, 22, minus the current length, L, which is some length less than the maximum. There is the difference of the maximum length and the current length, and we're told that the rate of growth is proportional, so we'll use a constant of proportionality, which is simply k. This differential equation states that the rate of change of growth is equal to a constant times the difference between the maximum length and the current length. This differential equation models the given phenomenon. There are methods for solving this differential equation to obtain the solution, which is a function that gives the length of the fish at any time t. We will not discuss how to get to this function in this video.